So I'm going to start out with just a short video, kind of summarizing the mission. And so let's do that now. And then
I think one of the age-old human questions, perhaps going back to the beginning of humanity, is are we alone in the universe? And that maps directly into why are we here?
OSIRIS-REx is 3 missions in one to make that kind of exploration cost-effectively for not much more than the price of a blockbuster movie.
There's been nothing like OSIRIS-REx in NASA's repertoire. I like to call it the Daredevil spacecraft.
And we have
We're going back to the dawn of the solar system. We're looking for clues as to why Earth is a habitable world. And of course, the biggest question, the one that drives my scientific investigations, is the origin of life. What is life? How did it originate? And why was the Earth the place that it occurred?
10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1.
okay, every time I watch that video, I get chills. It brings up a lot of emotions. It's been a roller coaster of a mission, and I'll explain a little bit about why as we go through this. So OSIRIS-REx itself is an acronym. NASA loves acronyms. Everything's got to be an acronym. And I'm going to focus mostly today on the O part, the origins. What are we learning about Bennu, about the origins of life, the origin of our solar system? But of course, asteroids are important for other reasons too. Folks mostly think about the impact hazard. Turns out Bennu is a potentially hazardous asteroid. And so part of the reason of going there is to learn more about its orbit so we can better predict where it will be in the future. Okay, so one of the theories about the origin of life is that the planet was actually seeded with the chemical building blocks of life, the organic compounds, and even water itself. Scientists today argue that the oceans came from comets and asteroids that brought that water here. This would have happened very long ago, roughly 4.5 to 4 billion years ago. And this is just a nice artist's conception of that. So why do we go to asteroids? Why do we study them? The truth is, if we're trying to understand how life started on the Earth, looking at the prebiotic chemistry, the organic chemistry that led to life, we can't learn about that here on the Earth. And that's because the oldest rocks on Earth, 4 billion years or so, have been altered by plate tectonics, Earth's giant recycling program, weathering, as well as life itself that's basically infested every rock. And so we really want to get a sample from the early solar system 4.5 billion years ago that's sort of frozen in time, that prebiotic chemical record. And so that's, at least from an origin of life perspective, that's why asteroids are so important to study. I like to go back to this one. This is a nice visual of the solar system. All of those dots, the smaller dots, the green and the reds are asteroids. Most of the asteroids are in the asteroid belt between Mars and Jupiter. At the time we were trying to select Bennu from those asteroids, there were about 500,000 asteroids. Now there's, I just checked, over 1.4 million detected asteroids. But we can't, it turns out it's very difficult to go all the way out to the asteroid belt to collect a sample. That's a very complicated robotic mission. And so there were only 192 or so back in 2010 that had orbits that were even possible to have a sample return. We also wanted objects that were large enough so that we could do a collection safely. The smaller asteroids that are less than 200 meters in diameter just spin too fast. So it's like jumping on a fast-moving merry-go-round. It can be pretty dangerous as a kid. Actually had quite a lot of fun doing that as a kid, but you don't want to risk a $1 billion mission on that. So we had to have an asteroid that was large enough. There were 26 of those. And then of those, there were only 5 that were carbon-rich, rich in carbon. And again, we're trying to answer this question about the origin of life, carbon-based organic compounds. We wanted an asteroid that was carbon-rich, and then we chose Bennu. Well, just how big is Bennu? About the size of the Empire State Building, a little bigger. Um, it would be a bad day if Bennu hit the Earth. Let's just say that. Fortunately, we know from predictions of the orbit of Bennu, and now after visiting it with the OSIRIS-REx spacecraft, it's a very low risk. So I think it's less than 1 in 1,800 chance in the late 2100s that Bennu could hit the Earth. So we can all sleep at night. There's no reason to be worried about Bennu hitting the Earth anytime soon. We launched in 2016. It took 2 years to get there, and right away we had our first big surprise. We thought Bennu, which is, you can see it down there in the bottom right, was going to be more like a beach sand, but it turns out there were a lot of big boulders, which makes sample collection and risky. And so the engineers were freaking out immediately as we got close. Oh my God, there's boulders everywhere. How are we going to be able to collect sample? To top it off, Bennu was literally spitting rocks at us. There were rocks, particle ejection events is what they were called. And we think it has to do with the heating of the Bennu from the sun and release of volatiles that were throwing these rocks at the spacecraft. Fortunately, they were traveling slow enough so it didn't present a hazard to the spacecraft. We were able to get very close, within 680 meters of the surface to get into orbit. We actually set 2 Guinness Book of World Records, which will probably stand for quite some time. So we orbited the smallest object in space and had the closest orbit. So as we were going around orbiting the asteroid, we were mapping it, trying to select the best site for the sample collection. And it's actually pretty cool what you can do with some of these instruments. So we were actually just from the reflected light. So we have these, they're called spectroscopy instruments. They can measure the reflected light. And it turns out that rocks, depending on their composition, will absorb light at different wavelengths. And so by looking at the absorption of the light, you can actually tell the compositions. Pretty cool. So right when we were at Bennu, we were taking these measurements with, it was called the OSIRIS instrument developed at NASA Goddard. We knew that the Bennu was loaded with clay minerals, which means a lot of water, and also carbon. We saw evidence for organic carbon. So we knew right away that we had picked the right asteroid to answer some of these science questions. So after mapping, we settled on 4 sites on the surface of the asteroid: Nightingale, Kingfisher, Osprey, and Sandpiper. The debate was mostly about engineering safety, safety to the spacecraft. So we wanted to find kind of these small craters that didn't have a lot of boulders around them. There weren't many spots that were safe, but these were the 4 that rose to the top, and we ended up selecting a site called Nightingale. And this gives you this is a recreation of the landing, the touch and go, what we call it, to collect the sample. You can see we're kind of going into the small crater here, Nightingale. And it was really threading the needle. So all of this had to be done autonomously because of the time it took for light, the radio signal. This was all pre-programmed. The spacecraft basically could, really thread the needle here, pinpoint kind of landing. It's akin to trying to, fit in between 3 parking places in a parking lot, but millions of miles away autonomously. So it was pretty scary. You see here that the solar panels are kind of slanted up because we were worried about dust getting thrown up. And then you see that arm, and at the end of the arm, there's the sample collector, which is something like, a 1957 Chevy air filter. It looks kind of like that, about that size. And so we touched down, and this is actual images of we call it the tag event. So on the right, you see we hit the surface, and then we actually blew nitrogen gas to kind of collect the sample inside this annulus, inside the collector. And you see these particles just going everywhere. And this was pretty actually unexpected. We expected to sort of kind of springboard off the surface of the asteroid. We thought it would be more, tougher. We actually had a spring that was designed after a certain amount of compression to trigger the backaway thrusters on the spacecraft so we could get out of there after the collection. Well, that spring never activated. And we just punched through the surface. We ended up going down about a half a meter or so. fortunately, we had another clock on the spacecraft that based on time, activated the backaway thrusters so we could get out of there. This was like jumping into like a plastic ball pit, the kind you find at, or used to have at McDonald's. And so fortunately, everything worked and we were able to back away. If not, we would have been dinner for Bennu. I mean, the spacecraft would have sunk into the asteroid. Just incredible, but everything worked well. We got the sample. The next surprise is that when we backed away from the asteroid and we were looking at the container, we saw particles coming out. It turned out that we had overfilled the container, and the flap that was designed to shut to keep the sample in, there was a particle, a stone wedged in there. And so samples were leaking out. And of course, the team sort of went into a panic mode. And it was like, every single particle was some scientist's PhD thesis, right, that we were losing. And so we quickly stowed it. The engineers are amazing, developed new scripts to get that done. You see it there on the right in the sample return capsule, closed it, and then came home. So it took 2 years after this to get back home, eagerly waiting the sample. We're supposed to land, or directed to land here in Utah near Salt Lake City, the Utah Test and Training Range, which is an Army facility. So not a lot around there, which is a good place to land. You see the landing ellipse there in red. We had an anomaly that was very scary. So I was actually out there with the media, and the parachute was supposed to open pretty quickly, actually, the main chute, and it didn't open right away. And so the SRC was just tumbling through the atmosphere, and that would have been bad because it would have been a hard landing. The sample return capsule would have broken open, samples contaminated. So we're all waiting for the chute to open, and there was this anomaly, but it finally opened late, and there was a big gas. I think I probably cried at that point because once we saw the chute, it was like, we've made it. We're finally back after this journey. And we even landed right near a road. It was pretty incredible. So pretty easy to go out there and collect it. Here you see actual footage of the precious asteroid material coming back to Earth. Wonderful day. And here you see it just sitting up perfectly, the chute heading away there. And then basically they flew out with a helicopter, documented the scene, made sure it was safe. There were some batteries that they had to make sure weren't leaking and that kind of thing, hazardous fumes. The sample return capsule was bagged. We wanted to, again, protect it from Earth contamination. We've got this pristine asteroid material, 4.5 billion years. The last thing we want to do is contaminate it with Earth stuff. So we immediately set up a purge there, you see in the top right, where we could purge nitrogen gas through to keep it clean. And then it was loaded into a C-17 and flown from Utah to Houston, where most of the sample is today. I love this picture. Just throw this in. The guy in blue there is Jason Dworkin. He's the project scientist who spent a couple decades working on this mission, putting his heart and soul into it. He's also the contamination lead, so I was very relieved that everything worked, but he was protecting the sample there in the C-17. So we landed in Houston. Again, the sample return capsule was transported to the Johnson Space Center, where they built a special curation facility to open up the canister and protect these samples, keep them clean. And I don't know if anybody was following in this, but when they were opening the canister, a couple of the bolts got stuck. They just didn't open. And because we wanted to keep these samples clean, you couldn't go in there with a drill like you do at home. You couldn't just drill through the screw. That was a no-go. So they had to develop a special tool that didn't use motors and was clean. And finally got it open, and it was like, oh my God, it was just finally a relief to see the actual asteroid material there. Very dark material. It's hard to explain. It doesn't look too dark here, but it's just really dark. It's some of the darkest stuff I've ever seen, actually, natural material. And that's because it's so carbon rich and rich in other metals. And we got twice the amount that we, our requirement. So our requirement was 60, we got over 120. Scientists love that because more sample means more science and more analyses. Rachel Funk was one of the curators who was one of the first to actually see the sample with her own eyes and work with it. She described it. Actually, they could smell it. Now, they didn't go in there with their noses and smell the sample. All this material was inside a nitrogen cabinet. But the tools that they used to scoop it, they pulled out, and they could smell the tools, the dust on the tools. It's a very strong kind of sulfur, maybe a gunpowder smell to it. There's described as burnt marshmallows. I never got a chance to smell it, so I'm not really sure. I'm just trusting them. But very dark, very sticky. Again, that's this organic kind of goop. And yeah, just incredible material. Okay, so this sample has now been distributed to over 200 scientists on the team, literally all around the world. I do want to point out that 70% of this material will not be studied. It'll be archived. And in fact, some of it is being frozen, sealed and frozen at minus 80 degrees Celsius to preserve it for a long time so that, 10, 20, 30, 40, 50 years, 100 years from now, somebody will be able to study this material, clean material, with a technique that doesn't even exist today. But we've got over 65 analytical techniques that we're using to study this material. Some I'll talk about in our lab at Goddard. That's actually me there in the middle picture, working there with a liquid chromatograph mass spectrometer. But some of the instruments that we're using, are the size of buildings. Lawrence Livermore, the synchrotron light source. You simply can't fly these, right? This is the benefit of sample return. You get these samples back to Earth, and then, we can study them with anything that we can put our minds to. So this is really the benefit. And as I mentioned, over 70% will be saved for future generations. And this was an exciting day. So this was a month, a little over a month, 6 weeks after the landing. We got our first sample at NASA Goddard. So that's our team there. Actually, these samples were sealed inside these stainless steel, call them Eagle stainless containers under nitrogen. So these samples have never seen air. So they're the least contaminated extraterrestrial material I've ever worked with, which is exciting. And so anyway, that's a photo of us in the lab getting ready to extract it. And so now I'm going to talk about some of the science questions that we're trying to answer here. We actually have 12 hypotheses. I'm not going to get into all of them, but the key scientists, we're looking to compare the sample to the spacecraft observations, kind of as a ground truth. And this will be useful for future missions that use similar instruments. And so we can kind of calibrate them, if you will, by studying the sample and comparing. Number two, this is what I'm most interested in. Do these samples have the building blocks of life, and could they have influenced the origin of life? But we can also learn about how the sample, what it tells us about the origin of the solar system itself, the history and evolution of our solar system. And then, of course, how has the sample changed since collection? We know you can never keep anything 100% pristine. There's always some alteration. And so we're looking at studying that as well. Sorry, I keep hitting the wrong back button. Okay, so how does the spacecraft compare with the observations? I talked about the clay minerals that we thought were present there from the spectroscopy, from the light measurements. And indeed, wow, we see a lot of phyllosilicates. 70–80% of this sample are these clay minerals. We also see iron sulfides, metal grains, which is pretty cool. Perhaps the sulfur smell is related potentially to some of these materials. These magnetite grains, again, another metal. Pretty cool. You see them in these, they call them rhomboids. I don't know who came up with that name, but these little spherules, really interesting shapes. These images are not from a microscope. This is a scanning electron microscope. It's a special microscope that can get really high resolution and up close images. We see carbonates, which is the source of some of the carbon, and again, hydrated and carbon rich. So actually, the spacecraft measurements told us we had about 1% carbon organic material. When we measured it, it was closer to 5%. So again, trying to ground truth and calibrate these instruments is really an important part of this. But basically, our predictions, for the most part, were correct with one exception. We found this phosphate, magnesium phosphate. You see it, this white crust, which we didn't see from orbit. This stuff only forms in kind of a salty ocean. And so this is pretty exciting because it means, the asteroid's parent body, the original parent body, was something more akin to, an icy ocean. So that this phosphate discovery was really, really, really exciting and something very unexpected. I'm going to move here now towards the organics. So I mentioned the carbon. We see organics all over the place. Some of these organics, they're called nanoglobules. So they actually fluoresce under ultraviolet light. And that was one of the first measurements we made. We actually took what's akin to a black light, UV light. It's kind of like the forensic science that, folks do in the crime scene investigation. And organic material will fluoresce or glow. And this stuff was glowing all over the place. So, just really incredible, again, organic rich. And then at Goddard, we made some measurements looking at some of the soluble compounds. So we actually took some of these samples, we boiled them in water, we made a Bennu, we call it Bennu tea. Definitely wouldn't want to drink this stuff, probably toxic. But in this water, we found ammonia, which was really exciting. Ammonia is a component of fertilizer, important for biological processes, and so we see quite a bit of ammonia. And we also see some of these other fundamental building blocks of life, like amino acids that you find in proteins. And we've seen this before. So on this chart on the left, we've seen these compounds before in meteorites, but what makes this measurement so special is we know Bennu is pristine. It hasn't been impacted by terrestrial contamination, so we can really trust these results. I get excited about that. And there's a lot more to come. So everything you've seen, were measurements made on, tens of milligrams of material. Now we've got almost 6.5 gram sample there that we've crushed up and powdered and split and sent to labs around the world. And so we're going to be looking for other building blocks of life, more complex chemicals, compounds that are present at really low concentrations that maybe we missed in the first pass. So this is really going to be is an exciting time right now. And I do want to just give a quick plug here. I didn't talk about everything we found. There's still some really exciting stuff, and NASA's going to have a media event at the end of the month on January 30th, a science live event. So please be sure to tune into that, and I can talk a lot. We'll talk a lot more about some of the discoveries. If you want to see Bennu for yourself, and you're in the DC area or have plans to go to the DC area, please visit the Smithsonian Natural History Museum, and you can see Bennu. It's there on the bottom left with your own eyes. And that's all I have. Thank you so much for your attention.